Well, hello, fellow Math 690 students. What a way to end semester 2020. This is actually the last class that I have to do and last project I have to do for me to finally get these 19 math credits that I've been so eagerly waiting for so I can teach college in the schools. But nonetheless, today we're going to be looking at complex numbers. And I specifically have decided to look at what complex numbers how they're used in economics and sales analysis. So, overview of Math 690. So what did we learn in complex variables and their applications? Okay, so we learned a whole bunch of stuff. So here's some of the stuff we learned. Obviously, complex number arithmetic and complex conjugates. We learned geometry, vectors, modulus, exponential form, polar coordinates. So far, those are the things that we probably would have seen in what we've done as teachers. For me specifically, I teach Algebra 2 and I teach pre-calc and calculus. So I've looked at those things, I've taught those things. So that was super easy when we got to that point. So I thought maybe this class was going to be, walk in the park in the beginning. But then we got to some other stuff, such as Euler's formula. Then we started talking about polynomial functions of complex variables and finding their roots. We talked about elementary mappings and functions, which again, we know elementary mappings and functions from Algebra 2, and we've looked at that, but now we look specifically at complex numbers and their mappings. We talked about limits and continuity, derivatives of functions, integration of complex numbers, which was super interesting. And this year is the first year I've taught calculus, so I had to brush up on that. So I was very thankful that I had brushed up on that for this class. And then we also talked about Cauchy-Riemann equations, contour integrals. Finally, we ended with Taylor and Lorentz series, and so much more in between. There was so much information, and it was super fun. I learned a whole bunch in this class. It went super fast, but I was very impressed with how much the amount of knowledge and how much math concepts we actually used during this entire class. So what's the big idea? The whole big idea of complex numbers is what? It's basically, it's the question that all of our students ask in Algebra 2 when we introduce imaginary numbers. We tell the story of imaginary numbers. We tell the story of Pythagoras and not believing that they are, and so much so that, he pushed someone overboard into a boat. If you haven't heard that story, it's super interesting. It gets kids engaged when we start talking about imaginary numbers. But nonetheless, what's the big idea? What are complex numbers used for? And so often for me personally, I say, well, if you're going to be an electrical engineer, you're going to be maybe an electrician, you're going to work with complex numbers. You'll work with imaginary numbers. We use J because they use I for current or impedance. So they use J, right? But it's the same thing. And so I'll ask questions like that on tests, real life application questions. And kids are like, well, I'm not going to be an electrical engineer, or I'm not going to be an electrician. I'm going to do something else. So my idea and my focus for this project was to find some real world problems that got away from electricity and got away from things that students wouldn't be interested in, but to do something that they would be interested in, something that they would be more something that a lot of them actually do go into fields of. So I did a little bit of research, okay, and I found some other careers that use complex numbers. In fact, at the beginning during the introduction time, that was my big question, was what are the applications of complex numbers? So I was very impressed, and I'm super excited to hear your guys' videos because I want to know what are some other applications, what are some other application problems. So 2 careers that I found were economists and sales analysts. And how do they use complex numbers? Well, economists use complex numbers when they're looking at business cycles and profit predictions. And we're going to look at what those are. And we're looking at an example, actually, of profit predictions that ends up having a complex solution. Complex numbers also might be used when economists look at something called the internal rate of return. And we're going to look at that equation. It's super cool, super interesting. And you definitely would get some complex solutions out of that. Next, sales analysts. So, a lot of students want to go into business in where I teach. They go into business and they look at different things. And so sales analysts use complex numbers when they make predictions as well. A lot of times profit predictions or something like that, right? And so a lot of the times what they'll do is they'll take data and they're going to form some sort of a regression model. And so when they're finding their regression models, they might have a solution that's complex. And so we're going to look at a problem that does that too. Now, economists. This is the business cycle right here. After doing some research, this is what it is. Now, the first thing I want to point out is that it is an oscillating cycle. You'll notice it's got oscillating curves right there, which we know that oscillating curves have complex solutions. Sinusoidal curves have complex solutions. So that's something that right away, we can see that there would be an application for complex numbers for economists, right? The other thing we want to talk about is internal rate of return. And here's the equation. Man, look at that equation. It's super interesting to look at. And so basically it says this. It says that your internal rate of return is some variable in an equation that summation is always equal to 0. And the first thing I thought of when I looked at this was the Lorentz series and the fact that they use a summation of a rational equation that has nth degree polynomials, right? And so going further into it and doing a bunch of research, I did find that this is used, and it's very similar to the Lorentz series, but it is used in complex numbers. But I have to be 100% honest, it's probably past my understanding of complex numbers in the complex plane. But having looking at it, it obviously does have sort of some sort of an application for this. And so basically it says this: if you start with some initial investment, and then you have a bunch of cash flows over some amount of time, it's always going to equal, its sum is always equal to 0, which is super interesting. And it would definitely be something that you would be able to solve for. If we just let that be an x, you'll notice that it's some sort of a rational polynomial of nth degree, and we could solve this out, very similar to when we talked about solving rational equations before. Okay? All right, so a sales analyst. So sales analysts often use regression models, and there's lots of different types. There's linear, exponential, inverse, and we're actually going to look at a problem, and we're going to look at each one of those for some sort of data, and they use that to predict profits. Now, when we're making regression models, and if you're in some sort of a statistics class like I am currently, or one that you teach, you'll know that correlation coefficients are something that's really important, R. And the closer it is to 1, the better it is at predicting and using our model, right? And so they're going to find, and they're going to use lots of different regressions, and they're going to get that number as close as they can to 1, right? And once they have that, then they can use that to solve for its roots, its x, and to get whatever they're looking for. Maybe it's the number of units according to something, or a year, or something like that. And obviously, you can tell that anytime you're using some sort of regression that isn't linear, you have the potential, especially quadratics or cubics or so on and so forth, or any nth degree polynomial, to be quite honest, you have the possibility of getting complex solutions. And so that is how they're going to use that. And we're going to look at a problem like that as well. So let's look at our first problem. Now, the first problem we're going to look at it's towards economics, right? And it talks about profit and predicting profits, right? So here it is. It says the demand equation for a microwave oven is given by little p is 140 minus 1/10,000th x, where little p is the unit price in dollars of a microwave oven, and x is the number of units sold. So as the number of units sold increases, the unit price is going to go down. Makes sense, right? The more you sell, the less it's going to cost. The cost equation is 80x plus 150,000. So obviously, as you increase the units sold, your cost is going to go up. Now, the profit would be x times the unit price. Okay, so the number of selling units, x, times the unit price minus the cost of production. So you're working in the marketing department. Again, this is an example of something that a lot of my students actually go into, is marketing, sales, business. You're working in the marketing department of the company, and you've been asked to determine the following: the profit function, the profit when we sell 250,000 units, and the unit price when we sell 250,000 units, and if possible, the unit price that will yield a profit of $10 million. So let's say our sales forecast for the year is $10 million. We want to figure out what that x value is if we want that profit to be 10 million. Okay. All right. So I wrote out some work here, and we'll go through it. So the profit function, we have to look at all three equations that they give us. First, the profit is x times the unit price minus cost. the unit price equation, and the cost equation. Okay, so the profit equation is our P of X. Okay, and so P of X, we just substitute in those values of our unit price and our cost equations, right? And so you'll see we have X, and so we can take X and my pointer here. We have our X, and we can distribute to 140 and to 110,000 X. We have 80X, and we distribute that minus sign, and we end up with this equation right here. Okay, it's quadratic. Obviously, it needs an extra 0 right here. I kind of screwed that up, but that's okay. And so you'll see we have a quadratic equation. Obviously, it's negative, which means it's opening down. So it's going to have a maximum number that it's going to find, right? And so now the nice thing is when we have that profit function is now we can just look at units sold. And now we get that profit based upon just X. Okay? Now, letter B, it says, what is the profit when we sell 250,000 units? So all we do is substitute in 250,000 units, and we end up getting 8.6 million. Okay, so you think, all right, so 10 million isn't too far from that, so it's got to be some number kind of close to 250. Maybe it's more than it, maybe it's less than it, but it's going to be around that number. Okay, so as an economist, you'd probably say, okay, I know that at 250,000, my number is probably going to be, you know, somewhere around that because here's 8.6 million as a profit. Now, the next is, what's the unit price then? Okay, so if we know that we want our profit to be $8.6 million, we have to sell microwaves at the cost of $115. Okay, sounds good. Maybe it's an expensive microwave, but let's be honest, I've looked at microwave prices that my wife wants me to get, and they're a lot more than $150. So, anyway, so we take this into account and we say, okay, so what can that unit price be? If we look at the question D, or part D of our question, and it says, what's the unit price going to be when we want our profit at $10 million? So again, we know that the idea of 250,000 units gives us something close to 8.6 million, or gives us exactly 8.6. So it's going to be something close to that, that'll give us possibly a value of X that will give us our unit price. So that's the idea behind it. The idea is that we're going to solve for X. Okay, we're going to solve for X when our profit is $10 million. So we set our profit equation equal to 10 million, right? And then we solve it like we normally would. Okay, we take it and we subtract 10 million from both sides, and we end up getting equal to 0. Now, we know that when it's equal to 0, we're lucky because now we can start solving for roots, right? And there's lots of different ways, and we're lucky this is just a quadratic equation, right? And so easiest way to do it, and this is something we did early in our class, is looking at the quadratic equation, right? We know for our values of A, B, and C, we can just plug it into our equation. And so I did that, right? And here's our values. 1/10,000, negative 1/10,000 is A. B is 60. C is negative 10,150,000. Forgot a 0, but again, I did it down here. And you'll notice that the discriminant, when we have two negative numbers, okay, and this is something that you probably talk to your kids about, when we have a discriminant that's both negative, generally what's going to happen is, unless our B is big enough, which in our case, it's kind of small compared to C, but unless our B is big enough, our discriminant is going to be less than 0, which means that we're going to have a complex solution, right? And in fact, when we do this, when we solve it out, we end up getting negative 460. So this is less than 0. Our discriminant is less than 0. So we know that our solution is going to be complex. And so I look at that. And if you look down here, we do get a complex solution, right? We actually get 300,000 plus or minus 10,000 I square roots of 115. So what does this mean? It means our solution is now a complex answer, right? It's something that is not a real solution. So if we wanted to solve that, or if we wanted to know what X is, it has an imaginary number. And so if we put that number into our unit price equation, it's going to lead us to something that, again, has a complex solution. And I actually didn't do that step on here, but again, you could with your students. And you'd find out that you get some complex number. So why is that, right? So let's look at some takeaways from this problem. We know that the root of the profit equation, when the profit is equal to 10 million, is a complex solution. So what does it mean? That means that A, we know that from our quadratic equation that we got, our profit equation is quadratic, and it's going to have a max height. And so we could solve for that max height, and it's going to be something bigger than 10 million, right? So what might an economist do with this findings? And to be 100% honest, this is a question that I, through research and different things, I couldn't know exactly. So here's some ideas of what I think they might be able to do. One thing we know how to do is we know how to write imaginary numbers as vectors, and we know how to find their modulus, right? And so if we do that, if we were to find that, we could relate that solution, which is a real answer, and so it takes an imaginary and puts it back in as a real solution, and we could take that and then use that to somehow relate it to a year that would make sense for this. Now, it might not line up with our profit equation, but it might be something, again, since we look at our business equation and if you remember back to that model, the business cycle, it generally tends up. And so we know that possibly that could help us find it. But essentially, what would an economist do? They would use their solution that's complex, and they would do some further analysis on it to get some sort of a real solution. Okay, now the next example we're going to look at is a sales analyst problem. Okay, we're looking at analyzing some sort of sales, right? So it says the sales S in billions of dollars for Texas Instrument in the year 2003 through 2008 are shown in the table at the right. Okay, so it says use a regression tool to find the model for the data, then graph it. Then from the graph determine when sales will be 15 billion, if is this possible, and then determine algebraically when the sales will be 15 billion, and is this possible? Okay, so for this I'm going to have to actually do a little bit of work, right? So for it, what I'm going to do is I'm going to look at this right here. Okay, so what I've done is I've popped this in. Okay, so here's our data table right here, and then it says to estimate X. We can't really do that, right? So I just put in 15 because that's when they want it equal to Y, but whatever. Okay, anyway, so if we look at this, and this is actually this is one I found online. It's kind of nice. The nice thing about this is that you can actually look at the different regressions and you can calculate them individually, right? And so if I do this, okay, if I do this linear regression, I can look at all the different types. You'll notice my correlation coefficient. And remember, that's something that's really important in statistics, is we want that number closer to 1, right? The closer to 1, the better the model is. And so you'll see that this is about 60, right? All right, so we're interested in this value right here. Okay, so I'll put a little star by it. That's what we're interested in every time. And we want that number closer to 1. So this is 60, so it's not very good, right? And in fact, below it, they show kind of what the graph is going to look like, and you'll see, it's not that great. There's more above than below the line. It's not a very good model, right? And we actually have sort of a trend going like that, right? Okay, so linear is not a good one, right? Okay, linear is not good. Let's try another one. Let's try logarithmic regression. Okay, so we take that, and what do we get? Well, a correlation coefficient of 708. Okay, so that's better. Not super good. It's not really close to 1, but it's getting there, right? And so we look at that, and okay, so it looks okay. I mean, it's all right. Okay, it's not great, but it's all right. All right, so then we go to the next one. We look at exponential regression, right? And I calculate this. And while I'm doing this, you'll see my correlation's down to 0.615, right? So it's, again, not as good as the last one. Okay, so we try again. Here's another type of regression, exponential regression. I calculate this. Okay, 615, not very good again. All right, power regression. So now we're looking at something to the B power, right? And so I do this, and 7.1, okay, not that great. Again, we're trying all these different things, and this is something that a sales analyst would do, is they would go through all these different regressions, right? And in fact, they probably have a lot more powerful things. I know Maple would have been a really good one to look at all the different regressions. Unfortunately, my calculator or my computer doesn't have it right now, but that's what it is. Okay. Okay, this correlation coefficient is negative, so it's not even all that good at all. Okay, so the only option we have is a quadratic regression. Okay, and so I look at that, and you'll notice when I do this, I get a correlation coefficient of 0.99. So that's really good. That's really close to 1. And so that means that we have a really good model. And actually, if you look at it, it is pretty good. It almost hits all those points exactly. And that's what we want, right? And so we get A, B, and C. Now, it's written in this form where A is actually the constant. For me personally, and I know probably for you, that would be C. So we kind of monkey around with that, but that's okay. And so we put these values in. We found our coefficients A, B, and C, right, in a quadratic thing. And so part B of this was to actually model it as a graph. So I go to Desmos, and if you don't use Desmos in your classroom, I would highly suggest it. It's super good. It makes graphs come to life almost for kids. It's so good, very colorful, very nice stuff, right? Anyway, so here is our equation, right? And I just rounded each thing to the nearest thousandth. But this is what we get, okay? We get this model right here, okay? It looks pretty good, right? The only problem is in part C, it says from the graph, when are we going to get 15? And you'll notice that our maximum value right here, our max height, is 14.2, right? Excuse me, 14.21. So according to this graph and according to our quadratic regression, the biggest value we can ever get is 14.21, right? And that's not 15, right? So according to this regression, we're never going to get it. So again, Texas Instruments never going to make $15 billion in a year. Now, that's probably not the case. It's probably that there is going to be a time when that happens, right? But according to this regression, that's not going to happen. Okay, so then if we go back to the problem, part C of it was to ask us how to solve it algebraically. Okay, and so that's what we're going to do, is we are actually going to solve it algebraically, right? So I did out the work here, okay? And so here's our function. It's the same one that we just looked at as a graph, okay, in purple. And we set it equal to 15 because that's what we want it equal to. Now, from the graph, it shows that it's not equal to 15, right? So but there's got to be a case when it does, right? So we set it equal to 15. We subtract 15 from both sides. Now it's equal to 0. Now we can find our roots. And so we do that. We use the quadratic formula, A, B, and C. Okay, again, we have two negatives. A and C are both negative. And again, you probably teach your kids as long as B is big enough, you know, two negatives actually normally gives us a discriminant that's less than 0. And in fact, it does. It gives us a discriminant of negative 1.44. So when I solve this whole thing out, our complex solution, or our solution is complex. It's negative 5.563 plus or minus 1.2i all over negative 918 thousandths, right? So again, this is not a solution that's in the real number. So what could we do? Okay, so we'll look at that, right? We're going to look at that right here. Okay, so our takeaways. It says that according to the quadratic regression model, that our sales will be 15 billion. When our sales are 15 billion, it's some sort of complex solution. So it's not something that we get without looking at something else. So what does this mean? It means that we don't have a real solution. It's not a real number set problem, right? So what might a sales analyst do for their findings? Well, for me personally, and I didn't write it out, but what I did next is I tried a cubic regression. And when I did that, I got a correlation coefficient very close to 1. It's 9.99, right? And you ended up having a real root. It was 37.5, right? Or something similar to that. And so when you solve that out, you do get a number, but it says it's 37 years later. Now, you might not be interested in 37 years later, right? But what this shows is that what sales analysts could do is if they solve out a regression that they think is really good and they get a complex solution, they can either A, like economists would do, maybe use some sort of a modulus and take a complex solution and transfer it back to a real solution and then use that to find our answer. Or maybe they try a different regression, okay? And maybe, again, if you did that cubic regression, one of them was real, but the other two were imaginary. And maybe you would do something bigger than that, power 4, power 5. And again, you're probably going to get maybe 1 or 2 real solutions, and they might not be solutions that are feasible. But then the rest will be complex solutions, right? So I hope that these are 2 problems that give you an example of something you can talk about in your class. For me specifically in Algebra 2, when it comes time to it, the next time around, when I'm talking about complex solutions, I'm going to have some great examples to talk about economists, sales analysts, different things I saw. Obviously, electrical engineers, that's an easy one, right? Quantum physicists, those guys, all those people. And again, these are quantum physics and electrical engineers are not a lot of things my kids go into, but those are examples of things that complex solutions do show up. And like it's been said in this class before, those are things that have been around in nature all the time, right? Those are things that we talk about or that we see and we deal with every day. Springs, electricity, electrical currents, waves. Those are all things that we deal with every single day. And complex solutions and complex numbers are super beneficial. So are complex numbers important? The final takeaway? Absolutely. And there's tons of ways that they can do it. And the cool thing is if you're really good at all of the applications in the real plane, you'll be super good at them in the complex plane. And the cool thing is there's enough really smart people out there that take a lot of time to make sure that we're able to do all of the same things, all the same sort of modeling, all the same sort of applications that we can do in the real world and the real plane that we can in the complex plane. So I look forward to seeing your guys' videos. I'm super excited to see what kind of problems you guys decided to choose, and I hope that you guys learned a little bit from mine. So thank you so much for watching, and good luck with your summer break.